All right. Well, hello everyone. I'm sorry that we're having to do our work this way, but it was going to be much too hot in the classroom, and you know the classroom's already warm as it is. So this is going to be the only solution we had. So um, we're going to work through all the stuff that we would have worked through tonight, all the stuff that I would show, the examples. We're going to do the practice problems, all that good stuff. When it comes to the now we're not going to take a break or anything. So, a normal 3 hour and 20 minute or a 2 hour and 50 minute class is going to really be condensed because we're not taking breaks. We're not leaving time for you all to do work on the problems. And so when we get to the problems that I'm having you all try, please, if you want, pause the video and then you can listen to my explanation after you work through the problem to make sure you're understanding it. And then play the video and you can see the actual work to see if it makes sense to you. Reminder to please text me or email me at some point this evening so I can put it down that you had attended tonight. Okay? With that, let's get to it. So we're going to talk about asymptotes and graphs for rational functions. We'll practice a little bit. Obviously not taking a break since we're doing this virtual. Then we're going to talk about nonlinear inequalities, and then we're going to work through the week 5 material. Okay? So what we're going to talk about is finding domains of rational functions, identifying vertical asymptotes, identifying horizontal asymptotes, finding the intercepts, and then graphing them, stuff like that. Okay? When we talk about a rational function, remember that a rational function, we've already talked about it before, a rational function is essentially just a fraction. And so an example of that is one that looks like this. Now this problem, for whatever reason, my iPad software does not like the f of x, and so this is really f of x. We don't have the 2 and the 3 really shouldn't be there, so that's f of x equals 2x plus 1 and 3x minus 4. Okay, so just realize that it's f of x, and that's going to be true the entire video that we're doing today because we're not we're using the software that just does not like the things that we're doing. So, okay. When we're thinking about the domain for a rational function, we need to think about and have the mindset that we don't want the denominator to be equal to 0. That's where the issue could come in with rational functions. Obviously, if there was radicals in there, then we would be dealing with it can't ever be negative. But most of the time, you're going to be talking about polynomial functions in the numerator and denominator, and you don't want those functions to be 0. And so in our problem that we have here, our denominator is 3x minus 4. And so we don't want 3x minus 4. We don't want that to be equal to 0. And so we would solve this just like we would any other function. We would add the 4 to both sides, and we'd get 3x equals 4, and then we would divide by 3. You get x is 4/3. And so that would help us set the domain, where the domain now would be we're going to go from negative infinity to 4/3 and union that with 4/3 to infinity. And so you do that, you look at every place that the denominator is equal to 0, because that's going to set your domain for rational functions. Okay? Graphs for rational functions, they deal with things called asymptotes. Okay? And so what asymptotes are imaginary lines that the graph does not cross near the edges. And so like this one will never cross over here, this will never cross over here, right? And this doesn't cross down here. And so when we're doing this is called a horizontal asymptote. I'm going to write that as HA. This is a vertical asymptote because that's the vertical line that doesn't cross. And so we would say that this horizontal asymptote is at y equals 0, and the vertical asymptote is at x equals 0. Okay? Now, we say that the graph never crosses it. Sometimes that's true. Sometimes it's not, especially around x equals 0. That could be an issue where we might have some things that happen in here at x equals 0. So if we get that kind of a situation, then it could cross over the asymptote right around there, around the origin. But most of the time, we're going to be looking at places that the function doesn't cross. Okay? Vertical asymptotes, what they come from is you get those from the denominator. And so what we're going to want to do is we want to factor and reduce. We want to set the denominator equal to 0 and solve for x. So just like with the domain, we're going to find values that make the denominator equal 0. That's going to determine our vertical asymptotes. For the horizontal asymptotes, okay, it's quite a bit different. We're going to say, one way you can do it is you could plug in a huge number for x and simplify. That's one way to do it. Or the way that I prefer doing it is find the degree of the numerator and the degree of the denominator. That information is going to tell you a lot of stuff. For example, if the numerator's degree is smaller than the denominator's degree, then your horizontal asymptote is at y equals 0. If the degrees are the exact same, then it's the horizontal asymptote is the ratio of the leading coefficients. And so the ratio of and this should be like the numerator divided by the denominator's leading coefficients. That's where you get the horizontal asymptote. And then finally, if the numerator is greater than the denominator, there is no horizontal asymptote. So you can use either one of these that you want. You could use plugging in there or using the ratio or using, the ratio of the degrees. But I prefer using this way because it's just so much faster. Because you can just look at it and inspect it and know really quickly. Okay, even when they're the same degree, and that you just use the ratio of the leading coefficients in order to be able to do that. So, like if it's a degree 4 in the numerator and the leading coefficient is a 5, and the denominator is also a degree 4 and the leading coefficient is a 4, then the horizontal asymptote's at 5/4. Okay, very quick, very easy to do. Okay, so let's try one here. So again, remember that when we're dealing with this, we're dealing with a situation where we're going to have these are that 2 and the 3 really aren't there, right? These are just pretend those are parentheses, okay? So when we're looking at this, first we're going to do the vertical asymptotes. So VA, vertical asymptotes, we're going to say this is x squared minus 1 equals 0. So we're going to add 1 to both sides, and we're going to say x squared is equal to 1. And then we're going to square root both sides, right? So we're going to get x is plus or minus 1. That means our vertical asymptotes are at x equals 1 and x equals negative 1. So those are two vertical lines that the function will never cross. Now when we do the horizontal asymptote, we're going to look, the degree of the numerator is a 2, the degree of the denominator is a 1. And so those are the same, right? So that's the situation where you have n equal d, numerator equals denominator. And so you're going to use the ratio of the leading coefficients, which in this case is 5/1. So our horizontal asymptote for this one is at y equals 5. Okay? All right. Let's practice this some more. So again, remember these are parentheses, knots, and it is so finicky, this thing. Interesting. All right, so let's say we wanted to find this. So first thing, we're going to find the domain. So we're going to take the denominator, and we're going to say the denominator can never be equal to 0, right? So we're going to say, let's do 2x squared plus x minus 1, and let's set that equal to 0. Well, if you notice, this is a quadratic function, right? And so we think, okay, well, maybe we can factor this, and we really can factor this, where this is 2x and x equals 0, right? And so we have, that's the leading term was a 2, the constant is a negative 1, so that means we're plus 1 and minus 1. And so if we want to pair that up with a 2, that means that this needs to be the plus, this needs to be the minus, which means that we would get solutions of x equals 1/2 and x equals negative 1. So that means that our domain now would be negative infinity to negative 1 union negative 1 to 1/2 union 1/2 to infinity. Okay? Then it says, now let's find the removable discontinuity. So we haven't talked about that yet. But what that means is that when you get more than just a linear function in the numerator and denominator, notice how both functions are quadratic. Okay, so we can rewrite this. The denominator now we know is 2x minus 1 and times x plus 1 because we did the factoring. The numerator, we can factor out an x because they both have an x in there. So it really can be x times 2x minus 1. Right? So now notice the numerator and denominator both share 2x minus 1. So really they get canceled out. When you get that canceling out, that's where a removable discontinuity will meet. And so that word removable discontinuity, that means a hole. There's a hole present in the graph. The hole is going to be present at x equals 1/2. Okay? But so then what we do now is we do the rest of the function, which is x over x plus 1, and that's going to help us find our asymptotes. First thing is we have to find the vertical asymptote, and so there's going to be a vertical asymptote when the denominator is equal to 0, so that means a vertical asymptote here is going to be at x equals -1 because that's the value that makes the denominator negative. The horizontal asymptote, we look at the ratio of the degrees. Those degrees are the same, they're both 1. We take the leading coefficients. The leading coefficients are both 1. So that means the horizontal asymptote for this is at y equals 1. Okay? All right. Let's go to the next problem. If we have, so we've talked about horizontal, we've talked about vertical asymptotes. Now there's things called slant asymptotes. So what that means is that if the numerator is 1 degree larger than the denominator, then what we do is we divide and ignore the remainder. So we're going to use our synthetic division, and we're going to do that division, and whatever we get out of it, regardless of the remainder, that's going to be our slant asymptote. And so realize that you have a numerator that's 1 degree higher than the denominator. When you do that division, right, let's say, for example, the numerator is degree 3, the denominator is degree 2. When you do that division, you have a 3 divided by a 2. That means you would get a linear function out. Slant asymptotes are always linear functions. Always. Okay? So let's practice one. So we want to find the asymptotes. So again, parentheses here. So we have 3x squared plus 1 over x. So first thing is, let's find the vertical asymptotes, right? So the vertical asymptote is where the denominator is equal to 0. That means for the vertical asymptote, that's going to be at x equals 0. Horizontal asymptotes, we're going to look at the ratio of the degrees. The numerator's degree is 2. The denominator's degree is 1. That's a 2 over 1. So since there's a 2 over 1, there is no horizontal. None. If the numerator is higher in degree than the denominator, you don't have any horizontal asymptotes. Now we have to find slant asymptotes. And so when we're doing the slant ones, we're going to do our division. So we're going to take 3x squared minus 1 and divide it by x, right? So that's what we're going to do, okay? And so we're going to go, and you need to do long division with this because we don't have a binomial. So we're going to take x and we're going to divide it into 3x squared plus 0x plus 1. Remember that 0x term is missing, so it needs to be in there, right? So we're going to look and say, how do we make an x? A 3x squared. We multiply by 3x. That's going to make 3x squared plus, well, that's it, 3x squared. Then we're going to do our subtraction. That goes away. We're left with a 1, right? And so that means that's our remainder because we can't make an x be a 1, okay? And so what that means is our slant asymptote is 3x, or you would say that it is at y equals 3x. There's our slant asymptote, okay? That's where you would have an asymptote that, because when we do this division, we would get 3x plus 1 over x. if we did that division, got the answer. But the only thing we're concerned about is the part that's not the remainder, so the 3x part. That's what creates our equation. We just set it to be y equals whatever we get, ignoring the remainder. There's our slant asymptote. Okay? All right, now let's move on to finding the intercepts. Okay, so for the x-intercept, again, like we've done before, we're going to let the y be 0. Okay, in this case, since it's a rational function, right, and we want the function to be equal to 0, we're going to set in order for y to be 0, you're going to make the numerator be 0. Okay, so you don't care about the denominator when you're finding the x-intercept. You only care about the numerator. And for the y-intercept, now you just make all the x's 0. Okay, and you find what you get for an answer. So let's practice that. Let's say we wanted to find the intercepts for this one. Again, remember these are parentheses. So for the, let's do the y-intercept because that's very easy. For the y-intercept, we're going to put 0 in for all the x's. And so what that would be is we would have 3 times 0 squared minus 1 over 0, right? And so if we do -1 divided by 0, we can't do that, right? So that means that there is no y-intercept. None. So this never crosses the y-axis. The x-intercept, just like it says, we would make the numerator be equal to 0. 3x squared minus 1 equals 0. Add 1. 3x squared is equal to 1. Divide by 3. X squared is equal to 1/3. And then square root that so you get that x is equal to plus or minus the square root of 1/3. There's where your x-intercepts occur. Is that plus or minus the square root of 1/3. Okay? So easy way of doing it. Just make the numerator be 0. There's your x-intercepts. Make x be 0. And calculate there's where your y-intercept is. Okay? If we're graphing rational functions, the first thing we want to find the domain. We want to find the asymptotes. And then we graph the asymptotes as dotted lines so we know where our graph is restricted to. And then you can create a table of values around the asymptotes to kind of get an idea about what's happening. Plot those points, right? And then you want to draw the curves, starting at the asymptote and then ending near another asymptote. In general, you don't cross the vertical asymptotes. That rule does not necessarily hold true. Well, I guess you don't cross vertical asymptotes ever. Horizontal asymptotes you can cross many times. It can happen many times near x equals 0, but you don't cross vertical asymptotes. Okay. And then the last thing is you're going to put in any required holes and check and make sure your domain. Okay? So let's practice and do that with this one. All right, again, parentheses here. So that's the function we just did. And so on that one, we know that the x-intercepts are at plus or minus the square root of 1/3, which that value is, so that's like 0.77 positive and negative. So those x-intercepts are very, very tiny and near the origin. So say that that's right there and right there. Okay? And so in this one, we had if you think about what the function was earlier, right, we had, we haven't done any asymptotes or anything like that, have we? We just found the intercepts. So let's find the horizontal asymptote first, okay? Or the vertical asymptote first. So the vertical asymptote, the VA, that's going to be where the denominator is equal to 0. That's at x equals 0. This thing is so finicky. It's frustrating. Sorry about that. It's just being a tickle. Okay, x equals 0. So there is a vertical asymptote right here that we're going to put in as a dotted line across x equals 0. Never going to cross that. Never going to happen. All that stuff's I'm going to erase this because I don't like the way this looks. All right. Dotted line. When my pen works, it works a whole lot better than my finger. The horizontal asymptote. So we're going to look at the ratio of the degrees. The numerator is a 2, the denominator is a 1. So there is no horizontal asymptote. We can find the slant asymptote by doing the division, which we did earlier back in a previous problem, I believe, right? Whoops. We did that much earlier. Let's see what it was. Yeah, so we found for this one the slant asymptote. Wow, this pen just does not want to cooperate. Was that y equals 3x. And so that means we're going to have an asymptote that's going to come across and going to be like this way. So diagonal, so it's going to be at 3x, 1, 2, 3 over 1. So it's going to be diagonal like this, and 1, 2, 3 over 1, 1, 2, 3 over 1, 1, 2, 3 over 1. So it's going to come through kind of like that. That's where our slant asymptote is. So you just draw that one in and to your graph, so you see it. So we're restricted along the slant asymptote. We're restricted along the vertical asymptote, and we want to just see what this function's going to look like and create from that. We know that the x-intercepts are at that 0.57, and the y-intercept, there isn't any, so we know it does not cross the y-axis. So that's going to help us to make that graph, because if we didn't know exactly where it was at, it would be maybe a little bit challenging to do, but we're going to try and make this graph, using all that information to be able to produce one that meets all the criteria that we have and that we could ever need for this graph. And so you're thinking about where the x-axis is, or where the x-intercept is, excuse me, and where there's no y-intercept, and that it has those slant asymptotes, and it has and it has a vertical asymptote at x equals 0. That's going to really kind of constrict what happens. And so you can kind of see this space, this area that I'm talking about, that has the function in it where those V's are happening, right? That's where it's going to happen. But it has to be able to interesting. So this, our problem was, it made, we said we found x-intercepts, and we said we had, but the restrictions that are happening on this are not very conducive to our space, right? Because we want to be able to have the two asymptotes, the vertical and the slant. We want to be able to make that happen, right? But we also know in the domain that x can never be equal to 0, right? We have that, so let's write that in there. So our domain Oh my goodness. It really is not liking me today. Our domain is that x can never be equal to 0. So we know that for sure. No horizontal. Slant asymptote at y equals 3x. I actually don't think that this actually reaches the value of... Well, the question is it on... where is this going to occur? Okay? And so if we put in a number, let's put in like x equals 1. Okay? If you put in x equals 1 into the numerator, you're going to get 3 times 1 squared plus 1 over 1. So that's 4 over 1. So we know that at 1, we're at 4. 1, 2, 3. So it's actually up here. If we put negative 1 in, we get negative 4. Because if we put negative 1 in, we're going to get 3 times negative 1, which is 3, negative 1 squared, plus 1. So that's 4 divided by negative 1, so that's negative 4. So at negative 1, we're getting negative 4 down here. So by using that, knowing that point, it actually does not cross our x-intercepts at all. Even though it says we have them, due to the restriction in the asymptotes, our graph never does cross that. So it's actually going to come and do something like, can I change this color? Let me see. Change this color. It's going to do something like this, like that, and like that. Because it's got to be restrictive along the asymptotes that we found. And so it's really, really, this is a really tricky one because we know we found x-intercepts, but due to the asymptotes, it's not going to cross. It's not going to get there. And so that's one of those situations where you want to substitute in a number. So I picked 1 and negative 1, and that showed me where it's going to be located, because it really could have been located in any spot in there, right? But by putting in 1 and negative 1, we figured out that it has to be in those two little v's. Okay, let's try another one. Okay, so again we have the problem where we have our parentheses here. So now we have 3x over x squared plus x minus 2. So first thing is, let's find what's happening with the denominator. And so this is where we want x squared plus x minus 2. That's going to give us our domain restrictions and our vertical asymptotes. So let's say equal to 0. That's a quadratic, right? So that's going to be x plus 2 and x minus 1 equals 0. That means that x is negative 2 and x equals 1. So that means our domain is everything except that x cannot be equal to negative 2 and 1. So those are only two spots for sure. So that means our vertical asymptotes are at x equals negative 2 and 1. Our horizontal asymptote, let's look at that. So our numerator is degree 1. Our denominator is degree 2. So when the numerator is smaller than the denominator, that means our horizontal asymptote is at y equals 0. Okay? So let's kind of draw this stuff in. So vertical asymptote at negative 2. So we're going to go negative 2 is going to get some dashed lines. Also at 1 is going to get some dashed lines. And then a horizontal asymptote at 0. Okay? So then we have a domain restriction of negative 2 and 1 that we'll never cross. That's why we have those asymptotes there. And so what we want to do is we want to kind of figure out what's happening with the function if we think about that graph, right? And so what the best way of approaching this is to kind of make a point that you want to see, test a point in order to see where it's at in the function. And if we can put in an x value that that'll show us where the y value is, then we can know for sure where it's at in this broad range of space that we have. Okay? And so, like, what I would do is I want to figure out what's in the space, and if it's in the very I want to figure out where it's at to the left of -2. So let's put in -3. Right? So if you put in -3, in the numerator you can get -9. In the denominator, you're going to get 9 minus 3 minus 2. So that's 9 minus 5. So you get 4. So you're going to get -9 over 4. That's a negative number. So that means in that left of that vertical asymptote at x equals -2, we're going to be below the x-axis. So remember, we're not going to cross anything. It's going to be like this. Okay? Let's figure out what happens to the right of x equals 1, the other vertical asymptote. So let's put in 2. If you put in 2, you get 3 times 2 is 6 in the numerator. You get 4 plus 2 minus 2, which is going to be 4. So we get positive over positive. We're in the positive. So this one's going to look like this, like that. Okay? Now the other thing we need to figure out is what's going on near in the middle. Okay? And so when we're in the middle, you notice, like, if we put in x equals 0, we're going to get 0 in the numerator and -2 in the denominator. So this is one of those situations you can cross the horizontal asymptote. You just can't cross the vertical one. So it's going to go through the origin. Now what we have to do is figure out which way is it going to happen. Okay? So we put in a value that's going to tell us if it's above or below the x-axis. And so let's put in like -1. You put -1 in the numerator, you get -3. In the denominator, you get 1 minus 1 minus 2. So that's going to be -2. So you have -3 over -2. Means it's a positive. It's above the x-axis. So your graph's going to look like this. And those middle ones like that always kind of look curvy like that. You just got to determine which way is it going. Is it making a shape like this, or is it making the one the opposite, the mirror image? Okay? So really, you just have to be able to find the domain. You have to be able to find the vertical asymptote, horizontal asymptote, put all that stuff in the function, but then you need to use test points to know where it's located so that you can accurately graph it. All right, so what if we are asked to find the function when we're given the graph? Okay, so that's a little bit of a different question. We're asked to find the function given the graph. So first thing is we want to use the x-intercepts and the multiplicity to get factors of the numerator. Okay, so the x-intercepts will give us all the factors of the numerator. We know by if it going through, it's multiplicity 1. If it touches, multiplicity 2. If it flattens out, multiplicity 3. Okay, the flatten out piece will keep going through, so that's either a 1 or a 3. That's what I'm getting at. And then the touch, the not cross, that could be 2 or 4. Right? It just has to be even. Okay? And then we're going to use the vertical asymptote to determine the factors of the denominator. It's going to give us that. And if it's a 1, it ends up going up, and 1 down, you have multiplicity of 1. If both ends go the same direction, you could have multiplicity of 2. Getting that kind of a situation, okay? So what if we said we want to find this function? Oh, and we can use any other point to get the stretch factor. Sorry about that. We need the stretch factor too. That's the a value. We need that. And so you're going to use another point to be able to do that. All right. So let's look at this function. Okay, first thing is, has x-intercepts at -2 and 1. And they both go through the axis. So that means that we know right away that we're going to start off that our numerator is going to have x plus 2 and x minus 1. That's what our numerator is going to have in there at first. Okay? There's going to be an a term possibly in front of that. So we need to kind of keep that into consideration. Now let's use the vertical asymptotes for the denominator. We have a vertical asymptote at -1, a vertical asymptote at +2. So that means we're going to have x plus 1 and x minus 2 in the denominators. Okay? At the x plus 1, both ends of the graph are going the same direction. And so since both ends of the graph are going in the same direction, that's going to be a multiplicity of 2. So that's going to be squared. The x minus 2, the ends are going opposite directions. And so that's a multiplicity of 1. Okay, that's how you kind of tell with the vertical asymptotes. So the only thing that we need to find now is the a value, right? And so what we would do is we're going to put in a value that we know that's on the function. Okay, and so what I would do is I'd say let's put in x equals 0, because at x equals 0, the graph crosses at 1. So we're going to say that 1 equals a, 0 plus 2 is 2, 0 minus 1 is -1, 0 plus 1 squared is 1, and minus 2. And so we get that 1 is equal to -2a over -2, which leads to a being 1. So our a value is 1. So what that means from all this is that our function, f of x, is just going to be x plus 2, x minus 1, divided by x plus 1 squared, x minus 2. Okay? There would be our answer. So again, you're going to use multiplicity not only for zeros, but also for vertical asymptotes. If the ends are going in the same direction, it's multiplicity 2. If they're going in opposite directions, multiplicity 1. Okay? No break. We're not going to do break. Now let's move on to nonlinear inequalities. Okay, nonlinear inequalities. So we're going to talk about finding critical numbers of nonlinear inequalities and then solving some problems. So when we think about nonlinear inequalities, first thing is we think about the steps to solve them, right? So first thing what you want to do is you want to make one side equal to 0, okay? This is going to be able to find the critical numbers, the zeros, and the undefines. And then you're going to pick a number that's on the line, on the number line, and you're going to pick test points and test them. So it's easy to do this if we just think about, let's do a problem, okay? So let's say we want to solve one that looks like this. So we have x squared minus 5x minus 6 is less than or equal to 0, or less than 0, okay? And so we can't just like move the 6 and divide by it. Can't do that because it's a quadratic, right? And so what we're going to do is we're going to factor the quadratic. And so the quadratic on this one is going to be factored into x minus 6 and x plus 1 is less than 0. So what that means is we have that their zeros are at x equals 6 and -1. So what you do is you go to a number line and you say, okay, at -1 is a 0, at positive 6 is a 0. And then what we're going to do is we're going to test points on the left of -1, between -1 and 6, and greater than 6. And we're going to see if there's solutions to the equation, because remember, we want it to be less than 0. So let's choose a point that's less than -1. Let's say we choose like -2. If you put -2 into the original equation, you're going to get, 4 plus 10 minus 6. So it's 14 minus 6, that's 8. That is not a solution because 8 is bigger than 0. If you choose a number now between -1 and 6, the easiest thing to choose is 0. That's going to be 0 minus 6. So this is a solution, that area. And then you choose a number that's bigger than 6. Let's say we chose 7. That would be 49 minus 35 minus 6. So that's 49 minus 35 is 14. Minus 6 is 8. That's less than 0. Or that's bigger than 0. Not a solution. So that means that our solution here, that's less than 0, because we don't want to include -1 and we don't want to include 6, because those are our zeros, is our solution would be, in interval notation, -1 to 6. That's the only range that we get a value less than 0. Okay? Let's try one that's a little more complicated. Okay? What if we do something like this? So we have 3x cubed minus 4x squared plus minus 12x greater than negative 16. Okay? So again, we want this to be equal to 0 first. So we're going to rewrite this and move that 16 over. So it's going to be 3x cubed minus 4x squared minus 12x plus 16 is greater than 0. So we're going to try and find the zeros of this function first. So we have to go back to our synthetic division, and we got to think about our factors, right? If we think about the P over Q thing that we did last class. So 16 would be, this would be plus or minus 1, 2, 4, 8, and 16. And then the denominator is 1 and 3, right? So we got lots of factors we can choose from. But let's just try, let's say we try x plus 1. Let's see if that's a factor, right? We put minus 1 in the box. So we go 3 minus 4 minus 12 plus 16. That's a plus, by the way. I don't really need the plus at the end, but I did that. Okay, so it's 3, negative 3, negative 7, 7. That's not going to work. I already see that's not going to work. So let's erase this. Let's try something else. Let's try x minus 1. So 1 goes here. 3, negative 4, negative 12, and 16. So it's going to be 3, 3, negative 1. That's not going to work. It's going to give us the wrong number. Okay. So get rid of that. Now let's try x plus 2. Negative 2, 3, negative 4, negative 12, and 16. So that's going to be 3, negative 6, negative 10, 20, 8, negative 6. There it is. So there's our factor. So x plus 2 is one of them. And then we also have down here in the solution 3x squared minus 10x plus 8. Right? So we got to think about factoring that one. Well, what would that give us? Let's see. This would give us 3x and x. And we want to make a minus in the middle plus, so we know they're both negative. It's got to be 2 and 4. So all the way get to 10. So your factors here now are the x plus 2 that we did earlier, the 3x minus 4, and the x minus 2. And we want that to be bigger than 0. Okay? So now we go to our number line. We're going to mark all those zeros. So we're going to have negative 2, positive 4/3, and positive 2. So again, we're going to test areas. So let's say we test left of negative 2. So I would use the factored form because that makes it easy. If we go like negative 3, the first one, the x plus 2 is going to be negative. The 3x minus 4 is going to be negative. And the x minus 2 is going to be negative. So you have negative, negative, negative. That makes a negative. So that whole area is going to be negative, not a solution. We want it to be bigger than 0. Let's choose a number between negative 2 and 4/3. Well, the easiest one to choose is 0. So if we choose 0, x plus 2 is positive. 3x minus 4 is negative. X minus 2 is negative. So that means that this whole area is positive. That's a solution because we want it to be bigger than 0, remember. Choose something between 4/3 and 2. So a little bit more than 1 1/3. Let's say 1 1/2. 1 1/2, the x plus 2 is positive. The 3x minus 4 is positive, and the x minus 2 is negative, so that whole area is negative. And then lastly, which is not a solution, choose a number bigger than 2. Let's say 3. 3x plus 2 is positive. 3x minus 4 is positive. X minus 2 is positive. This whole area is positive. So we have two areas that are a solution, and it's greater than but not equal to 0. So that means that negative 2, to 4/3 is a solution union with 2 to infinity. Okay? All right, perfect. So now let's review some of the stuff we've done this week. Okay, and again, we're not going to do all these, but just kind of reviewing some of the material we did this week. So first thing is we use Russell's theorem to help us solve the polynomial equation. So let's say we did, let's do 34. That's the most complicated one of them all. All right, so we're going to do P over Q. Whoops. And it helps if I choose my pen. So P over Q is going to be, we have the 12 for the P. So that's going to be plus or minus 1, 2, 3, 4, 6, and 12. And 4 is going to be 1, 2, and 4. So we got lots of factors to choose from when we do this. So, again, we're going to be smart when we do this. Because you think about the Karts rule with this, we're not going to have, there's no sign changes. So with no sign changes, we're never going to have any positive real factors, since everything in here is a positive number. So we need to have only negative real factors without any sign changes. So that means we can skip all of the positive ones. That means skip all the ones that are x minus, because those are positive factors. Okay, so we only want the ones that are going to give us good solutions. Okay, and I'm going to kind of just skip a little bit, because we could try a whole bunch of different things. Unfortunately, with this one, we're going to have that one half is a factor, negative one half is a factor. So that means if we did the synthetic division, we would put in, it'd be x plus one half, which means we would use negative one half in the box. So we haven't done one like that yet, but if you tried all these problems, you would see that negative one half was the only one that worked. Well, there's actually two that work with this. And so we do negative one half. We put 4, 8, 19, 32, and 12, which leaves us with, this is going to be negative 2, and 6, and negative 3, and what's that, 16, and negative 8, and 24, negative 12, and 0. Okay, so you could have done all the trial and error, but x plus a half is one of them that works. And then we also would have that x plus 3 halves would also work. You can use that with the one we just did with this function. And so we put in negative 3 halves in the box, and we have 4, 6, 16, and 24, which means that we would have 4, and negative 3 halves times 4 is negative 6. So that's 0, 0, 16. That's 48 divided by 2, which is going to be negative 24, and 0. And so that means we're left with 4x squared plus 16 equals 0. Well, that's not factorable, and that actually produces imaginary roots. So we'd have 4x squared equals negative 16, or x squared equals negative 4, or x equals plus or minus 2i. Right? So our solutions here are x equals, put it up here on the top, negative 1 half, negative 3 halves, and plus or minus 2i. Okay? So that was 34 that I did. Lots of those in there you can practice if you want. 31 and 33 would have solutions in the book if you want to look at those. Okay? Just really quickly, let's review Descartes' rule of signs. So I could do 36. So Descartes' rule of signs, you look for sign changes first. So there's one, there's one, there's one, there's one. So 4 sign changes, so that means that positive ones, we would have 4, 2, or 0. And then for the negative one, remember we put in negatives for the x. So when you put negatives in for x, you're going to get 2x to the 4th plus x cubed plus 4x squared plus 5x plus 1. Notice no sign changes in that, so there's no negatives. Okay? Practice 35 if you want to with that some more. Okay, let's do 38. We want to find the intercepts in the vertical and horizontal asymptotes. So vertical asymptotes, remember that's the denominator. That's where the denominator is equal to 0. And so for this one, we would say that x squared minus 4 equals 0. And so that's x squared equals 2, which means that x is equal to plus or minus the square root of 2. So those are our 2 vertical asymptotes. And then horizontal asymptotes, the degree on 38 are the same. The leading coefficients are both 1. So a horizontal asymptote for this one is that y equals 1. The intercepts, the y-intercept, we make x be 0. And so if x is 0, we're going to have 1 divided by negative 4. So the y-intercept is going to be at 0, negative 1/4. The x-intercept, we make the numerator equal to 0, so we're going to say x squared plus 1 equals 0. Well, that's going to be that x squared equals negative 1, so that means there's no x-intercept because that's going to be an imaginary number. Okay? And then we could sketch a graph from all that stuff if with that information we have in there. Knowing that we have at 1, 2, 3, 4 like this, and if we change, we want to go 1, 2, 3, 4, 4. So if we graph this, we would have a vertical asymptote right there, a vertical asymptote right there, a horizontal asymptote at y equals 1 right there, right? There's no x-intercept, so we know we're not going to be anywhere near the x-axis. So we're going to have, if we did this one, you would have, let's see what happens when x is 0 at negative 1/4. So that's down here, right? So when that's down there, that means that we're going to have a graph that kind of does something a little different. It's going to go like this, there. And these ones, since we can't touch the x-axis, they got to be like this. Otherwise, they touch the x-axis. That's what the graph would look like. You can always check it with Desmos, right? Okay. And then let's try and practice finding the slant asymptote one more time. So I'll do 42. So slant asymptote, that's where you're doing division. So we're going to do something like x squared plus 1, going to divide that into 2x cubed minus x squared plus 4. So your memory, when we do this long division, you look at the first term and the first term. So how do you make x squared be 2x cubed? You multiply it by, oops, I forgot something in there. I forgot that we needed to have a plus 0x plus 4. We have to multiply it by 2x. And so 2x times 2x, or times x squared is 2x cubed. And then plus 2x. Do that subtraction, we get negative 3x. Whoa. That is not aligned right. Back it up. Back this up. Back it up. Okay. So 2x times that is 2x cubed. There is no x squared, so we really need another one here too. So let's make sure we have all the pieces in there. before we do this. So it's going to be an x squared plus 0x plus 1. And that's going to make a 0x and then plus 2x. Now we do our subtraction. We get negative x squared minus 2x plus 4. So how to make an x be a negative x? You'd multiply by negative 1. So that's negative x squared plus 0x minus 1. That means our remainder is going to be negative 2x plus 5. But we don't care about the remainder. Slant asymptote here is y equals 2x minus 1. There is your solution. Okay. Last thing is inverses. So remember, we want to try and find the inverse. Just kind of review. Let's say we did like 44. So we're going to find inverses. You're going to take and you're going to switch the x and y. So this is going to be that x is equal to y plus 4 squared minus 3. So we're going to solve that for y. So it's going to be x plus 3 is equal to y plus 4 squared. We square root, and we're going to get plus or minus x plus 3 is equal to y plus 4. That means that y is equal to plus or minus square root of x plus 3 minus 4. There's your inverse. Now remember, we want x to always be greater than negative 4 in this situation. And so when we make that be greater than negative 4, you have to choose values that are larger than negative 4, which would be like, actually we need it to be greater than negative 3 because we can't have this radical that we got for an answer to be less than 0. So when we do that, we would get that this would be our inverse. But we would say that x has got to be greater than or equal to negative 3. Right? There's a restriction. Okay? And then let's say we did 46. We'd say x is equal to 2y cubed minus 3. Add the 3, so you get x plus 3 is equal to 2y cubed. It means that y cubed is equal to x plus 3 over 2. And then you cube root it so that y is equal to the cube root of x plus 3 over 2. No domain restriction for this because it's a cubic function. It's not a square root, so we don't have to worry about that. Okay? Reminder of assignments this week. You have your discussion post that's due tonight, so make sure you get that done. Remember, it's Sunday at midnight. You need your 2 replies to your classmates. And then you have homework from sections 3, 6, 7, 8, 9, and 10 that are all due on Sunday at midnight. No quiz this week. Next week, we will finish Chapter 3, and we'll have our quiz next week for Chapter 3. We have one more section to do in Chapter 3 before the quiz. Okay? Hope you enjoyed this version of doing it. I know it was very fast, but use the videos in the questions to also support you and enjoy your night off from class.